Hi everyone, my name is Richard Applewhite. I'm Work Package 1 leader. I'll give a short introduction into the work package and then hand over to my colleagues, Felicia and Gregoire. So we've been asked to, as a company, so I'm from Ineos Synovin, to be involved in the HyPSTER project. So outside of the HyPSTER project, my day job is technical manager for Ineos Synovin. We're concerned with production of brine for feedstock, but also a number of gas storage projects. So we've worked with a number of partners on gas storage projects previously. So that's me. Okay, so work package 1, what's it about? We looked initially at the energy production, the renewable energy production available in the context of EZ53, so in the region. We tested assumptions on the sizing of the electrolyzer that we've heard described. We also looked at, obviously, the demand profile for hydrogen in the region. And then finally, looked at what that looked like, for cyclic testing to inform the actual test program of Work Package 3. So without further ado, I'll hand over to Felicia. Thank you.
Great, thank you very much. Hi, I'm Felicia Chang. I'm a managing consultant at ERM, and we led the first half of this work package, so trying to understand kind of the theoretical potential cycles of interest for the cavern. So in terms of the high-level results for this work package, we looked at how salt caverns could be used to support daily and seasonal variation, both on the supply and the demand side, as well as providing backup services. And that led to the profiles that you may have seen before, which Gregoire will talk about further shortly. Obviously, there's a wide range of potential supply and demand profiles that hydrogen could be used for, with the low carbon hydrogen sector still growing. So that was a challenge to incorporate all of the different profiles that we might want to consider, and then, of course, translate that practically into testing for EZ53. So just to give an initial picture of what we were looking at, we set up a project configuration where we had our salt cavern connected to renewable electrolysis from renewable electricity, considering different types of electricity supply, and also different types of hydrogen demand. We considered, so the renewable profiles, we looked at solar, wind, and hydro generation, and that was really dominated by the seasonal variation in these different generating profiles, particularly, of course, for solar and wind, but we also considered kind of the daily fluctuation. So we modeled them on an hourly basis over the course of a year. On the demand side, we considered a few different demands. So one of them is hydrogen for heating. This shows domestic heating, where we see quite a big seasonal swing. Obviously, this is going to depend on where you are in Europe, and also heating technologies differ depending on where you are in Europe. But if you are using hydrogen for heating, you can expect to see quite a big seasonal demand, with less demand in the summer compared to the winter, and quite a big daily spike as well. So there's kind of these short timescale and these longer timescale swings to consider. We had a look at mobility as well, where we expect to see quite a big daily change in demand as you're kind of refilling and filling tube trailers, and cars will have a more consistent profile, although of course that could be buffered by on-site hydrogen storage at the refueling station as well. And not shown here, but so that was domestic heating. Of course, industrial heating could have quite a different profile. Again, more likely to see much more consistent demand for industrial profiles across the whole year, which would then need to be matched with that variable renewable supply that we looked at earlier. So this is just one example. We have many examples of these, of what a salt cavern could be doing in one of these theoretical cases. So we've got the salt cavern filling through the winter months, because this is using wind, where there's higher wind generation in the winter, and then gradually emptying over the course of the summer. However, you can also see there's lots of small fluctuations on that graph as well, which really highlighted the importance to us of doing those different time duration tests, which I think informed the profile that we eventually landed on for EZ53, which Grégoire can talk about more.
Yes, we imagine from this basis, we imagine the use of the storage. So we develop some software calculating the consumption and on the basis on the production and the consumption, we calculate the stock in the cavern day after day, and to have period with storage and period with withdrawal, and to check if we have filled all the cavern with hydrogen, how we can propose for hydrogen storage quantity day after day and so on. And we also have contact with industrial in the area to have an idea of their needs of hydrogen. And so we develop from this with these equipments, the idea, I already show you your slide, but the idea to work with the cavern. There is limitation in our experiments because we have a small quantity of hydrogen, and we have this opportunity to simulate the cycling of pressurization and depressurization, as I already show. And for that, this configuration imply a limitation due to the maximum and minimum pressure we can have by this system of brine injection and withdrawal. So we have a possible range of pressure to test. And finally, we arrive to this design of test with this superposition of cycles, something representative a daily use of the storage for small quantity, for example, due to the production with for photovoltaic panels, and also for use because there is a daily use, day and night use. So that's the reason why we have these small cycles, and the superposition with something more seasonal because we saw that we have a seasonal production with renewables, for example, with wind, where there are more wind in summer than in winter than in summer, and so we try to test things representative of this possible use of storage. So daily cycle, small quantity, and larger cycle, more seasonal. So that's the reason we arrived to this superposition of small cycles and larger cycles. We repeated 3 times, and then at the end of the experiment, because it is an experiment, we use all the capacity with at least 10 cycling to the total range of pressure we can use. And finally, the final withdrawal is also representative. The idea that we withdraw all the capacity of a cavern in one time. For example, because the winter is very, very cold and we need to heat something, maybe with hydrogen, or if we, I don't know, imagine that all the electrolyzers are off and we have to compensate this production by withdrawing all the cavern. So it is like this that we design finally this test we will do now, tomorrow. Yeah. The only point for the specialist is that we have a system with water inside the pipe at the end to increase a little the range for this final withdrawal. It's a way to play a little on the density of the fluids inside the cavern, which allow to win about 20 bar, switching from brine to water. And so we have a final withdrawal with a small larger range than from the cycling. But it is a question of specialist. yeah, all that is to project to develop something and to replicate finally the storage. So to have an idea of what we will need, we will test things inside the cavern, and we have really used this different profile to have a good idea of what could be done inside a real cavern, a real storage. And we have to pass from the experimental cavern, Z53 is a tiny cavern, and we fill a small quantity of this tiny cavern to a big cavern and to develop the tools to design things correctly. And so for that, we have to validate our tools on this experiment, and then we can use this tool for design the other development of a large scale salt cavern.
Yeah, I think that's all. So if anyone has any questions, we'd be happy to.
Thank you. So yes, we have time for 1-2 questions.
Thank you for this presentation. I'm Louis Lond from Geostock. I have a question about the testing program, the cycling test program. Your CEO mentioned that it's very important to have a frequency, which makes sense. I think this is well designed. I understand why you did that. My question is, can you demonstrate, or how did you intend to demonstrate that everything went well? Are you going to focus on the cavern itself? I mean, by checking the volume of the cavern at the end of this cycling procedure? Are you going to focus on the materials and check that there is no fatigue effect on the steel? Are you going on the packers, etc.? What are you going to check afterwards?
Yeah, it's a difficult question, in fact, because in an experiment, we have to make choice. And a lot of things could be interesting. For example, it could be very interesting to, after withdraw all the hydrogen, to remove the completion and to check the state of the completion. But it's difficult to do. It's relatively expensive. And the question is what we can do with the cavern. So if we want to use it for storage, I will let the completion inside. So I have no occasion to check the effect of hydrogen. And in reality, I imagine that if I can have a problem of fatigue or a problem of embrittlement or so on in the completion, finally 3 months, it's very short. So it's probably not possible to control everything, especially on long term, because the experiment is short, to be sure to have something representative of the future for big cavern for long term. So we tried to design things to get the best of the experiment, but for sure there are a lot of questions we will continue to have, because, for example, on the cavern, we fill a small quantity of cavern, and the behavior of hydrogen, thermodynamical behavior of hydrogen inside the cavern, because of the size of the cavern, because of the quantity, it's too small to get something very sensitive to be representative for a big cavern where the time of equilibrium will be longer and so on. So we'll check things. For example, the creep of this cavern is very small. We had a sonar survey from the beginning of the 80s when the cavern was leached long time ago, and we did a new sonar survey last year in 2023, and the difference is under the uncertainties of the measurement. So no creep for this cavern. The cavern stay idle. There is no big solicitation of this cavern during these 40 years. But so it's difficult to imagine to have a new sonar and say, oh yes, we see the effect of something because it's too small, too short in time. And so of course it will be difficult. what we will really show that it's possible to have this pressure variation, that we have the good quantity of hydrogen. There is no unexpected evolution of the quantity of hydrogen inside the cavern when we inject, withdraw the brine. It is the configuration of the first filling, so it's also interesting to have to see if we have an evolution in the tightness if we have hydrogen going inside the central tubing and things like that. But we have only 3 months, so it's relatively short. And so it is always the limitation and the frustration of the researcher to have this experiment, but to not be able to answer all the questions we should have.
I will be relaying for Olivier through the chat. Hello, very interesting presentations. 2 questions. In the future operation, would the dewatering head be present permanently, and would you be able to inject and produce at the same time?
Yeah. For this experiment, we have this wellhead, and we will keep the central tubing for brine withdrawal, injection and withdrawal. Of course, normal use of a cavern is to fill all the cavern and to have what we call a snubbing, to remove the central pipe and to work only with pressurized and depressurization of the hydrogen. It's what we used to do with natural gas. Today we have not decided what we will do with this cavern. Do we have to use it for a storage, but it is a very small storage? Or do we have to develop a new big cavern, so with a new completion? We have no decision today. It's probably too early. But what is interesting in this case, with this specific completion with an anolis safety valve, it's possible to work with a cavern filled with half of the capacity, and to start to operate the hydrogen, inject, withdrawing, with the same level of safety than with a classical cavern with just one safety valve, because we will have an underground safety valve keeping the brine pipe inside. So it's possible to develop a first step with half of the capacity, for example, without snubbing, to start to operate the gas, and then after that, probably if we have new needs or we need more capacity, to continue to fill the cavern, and then maybe to have this snubbing to remove the central pipe and start to operate it. So both are possible, and it's also possible if we want to replicate that to a big cavern, to say that I fill a third of the capacity because the needs are only for a third for first time, and then to develop more capacity with time until fill all the cavern and remove the central pipe. I hope this answers the question.
Thank you. So I think we'll move to the other presentation. Thank you for your presentation, Grégoire, Felicia, and Richard.